welcome to this lecture. In this lecture, we are going to analyze the tubular heat exchanger double pipe type in details. So, already we have talked about the double pipe heat exchanger in one of our earlier lecture classes, and we know that how it looks like, and it is a tube in tube heat exchanger. It can be arranged either in counter current heat exchanger mode, or it can be arranged in the parallel flow. Fluid streams can be arranged in the parallel flow mode. So, if we look into this construction, either it will be as it has shown that the fluid is entering from, both the fluids are entering from this end and this end, and they are constituting a counter current arrangement. Whereas, if we put this flow from this end and this flow from this end, it becomes a parallel flow arrangement. Now, looking into the construction of this geometry, we see that these two are the support structures to keep it in position, whereas these are generally flanged connection. So, if we remove this part, we are able to clean this heat exchanger easily. So, that gives a pretty good advantage for this type of exchangers, that we can clean it easily and we can use it for dirty environment, or the fluids handling dirts can also be used for this in this exchanger. So, this is the schematic one, and we have already talked about it. Advantages, it is ease, we have the ease of cleaning, we have the advantage of using this exchanger where we need both the fluid streams are of extremely high pressure, or one of the fluid stream is of extremely high pressure. On the negative side, we have generally typically small surface area associated with this one, and we have relatively bulky and bit expensive. This is per unit surface area. If we look into, it is bit expensive. So, now if we go into the design part of it, we will find that this exchanger can also be connected in series mode, or they can also be arranged in the parallel mode. Like here we see just one after the other, the heat exchanger has been connected, two hairpin heat exchanger has been connected in series. It means that one end of the exchanger, the fluid is entering from this end, and then it is taking a turn, then coming out, and then it is going and entering to the second hairpin. Similarly, the other fluid, if we look at, we will find that this fluid stream is coming from here, coming from this end, and we have an external connection to put it in the second heat exchanger. So, like that we have, this is the entry, this is the entry and this is the exit, and here this is the entry and this is the exit for the other fluid stream. So, this is in series, both the fluids are connected in series. So, we have also the option to put them in the parallel mode. So, in parallel mode, what happens? One of the fluid stream will be divided into two parts. Say for example, so one of the fluid stream is coming over here, it is divided into two parts. One part is entering to this fluid stream and it will carry on like this. The other part will be distributed to the second hairpin. So, this is entering here, this is entering at this point. So, that is how it is getting divided into two. What is about the other fluid stream? The other fluid stream, if you look at, it is entering from this side, it is coming over here, this is coming over here, and this is getting distributed to this end, and also it is coming like this, and finally it is this will move out like this. But what is about the other fluid stream, how it is moving out? This is coming over here, this will move out like this. Let me just look once more. So, this is coming over here, getting distributed into this and this. This will be coming like this fluid stream. If we look at, it will come like this. Similarly, this fluid stream will come like this and come out like this. So, we have the other fluid stream which will follow this path in the tube, and it will be getting distributed and finally come out from this end. So, that is about the hairpin which is in the parallel mode. Now, if we look into the analysis part of this double pipe heat exchanger, for the inner pipe or for the inner tube, we have already we have talked about this heat transfer coefficient. For the inner tube, we have Fe F equals to 64 by Re, and the delta P is related to this friction factor by this relation FLG square by 2 rho dH, whereas the Nusselt number is given in terms of the Grach number. So, this is for the laminar flow. This is similarly, I mean, the same thing is valid also for the inner tube. For the turbulent flow, we have talked about this kind of heat transfer coefficient, and this is valid for this case. So, there is as such nothing new for the inner tube, whereas the other part is the annular part, where in the annular part we have this heat transfer coefficient. If we want to look for, or the heat transfer coefficient and the pressure drop, we have basically same correlation, but evaluated in terms of a different hydraulic diameter or equivalent diameter, often we call. This is the equivalent diameter, this is the hydraulic diameter. Already we have talked about the hydraulic diameter. This is the hydraulic diameter. It is defined as 4 times the free flow area divided by the weighted perimeter. What is the weighted perimeter? Weighted perimeter is this surface area and this perimeter. So, where the fluid is coming in contact to this surface, as well as it is coming to this surface. So, this is where it is weighting the perimeter, and that we have to take into account. So, this is the inner diameter is this is the outer diameter of the inner pipe, and this is the inner diameter of the outer pipe. So, it is connecting both the outer diameter of the inner pipe and inner diameter of the outer pipe. So, this is what is the weighted perimeter, and this is the definition we are familiar with for the hydraulic diameter. Now, we have another diameter here which is defined in terms of the heat transfer perimeter, and this we call it as hydraulic equivalent diameter. This equivalent diameter. Now, what is the heat transfer perimeter? The heat transfer perimeter, the heat transfer is occurring in terms of only through this area, because we have the inner fluid flowing through this tube and the fluid flowing at the annular space, another fluid. So, the heat transfer is taking place through this surface, and that is related to pi d0. So, d0 is the external diameter of the inner tube, and we define the equivalent diameter by the 4 times the net free flow area. It remains the same. This is the net free flow area and this hashed part. So, this hashed part is basically the net free flow area divided by the heat transfer perimeter, and that is how we will be getting the equivalent diameter. So, these two terms will be coming, otherwise the same correlations can be used for the annular space, except that we have to use this hydraulic diameter or the equivalent diameter for the appropriate calculation. So, we will look into that, how do we do that. Now, in case of laminar flow in the annular space, we have the following relations. We have taken it from the Encropeda and David book, and the laminar flow region is still defined by RE less than 2300, and when we have this is d0, this is d0, this should be di. Now, d0 by di, as this ratio is increasing, we have the inner, Nusselt number corresponding to the inner tube as well as this Nusselt number for the external tube. So, we are not really interested about this part, because we are assuming that this will be insulated and this tube, the heat exchanger part will be insulated. So, we will be mostly interested about these figures, these numbers, but this is when the flow through the annular space is laminar in nature. So, you may be remembering that in one of our earlier class, when we were solving the first numerical problem in connection to epsilon and n tube, we have solved a tube in tube heat exchanger, and during that time we have tried to solve the heat transfer coefficient of that annular space H0, and there we have used this one of these equations from which we have estimated this H0. If you go back to your earlier lectures, you will be able to correlate it with this one. So, now if we look at the other flow regime, that is the turbulent flow regime, we have the same correlations which we have said for the turbulent flow in the inner tube can also be applied for the annular space, but this is another heat transfer correlation which is which can be used either for the inner tube or for the annular space with the appropriate hydraulic diameter. And here this is related to the friction factor given by this 1.58 ln Re, etc. So, we will make use of these correlations while solving the numerical problem. So, based on this analysis, now we will try to solve a numerical problem where we find that water with a flow rate of 500 kg per hour is heated up from 20 degree to 35 degree centigrade by hot water at 140 degree centigrade, and there is 15 degree temperature drop allowed with the water, and we have 3.5 meter hairpin of 3 inch by 2 inch. So, by saying this one, we have specified the outer diameter, and also we have specified the inner diameter. Look, we have been given the inner diameter OD and ID both. So, it is a counterflow double pipe heat exchanger with annuli and pipes, each connected in series. So, this is important, and hot water flows through the inner tube. So, now we know that we have a double pipe exchanger with the inner one is having the hot water and outer one is having the cold water. So, this warm water, with the warm water 140 degree is the entry and 15 degree temperature drop is allowable, whereas this cold water has to be heated up from 20 degree to 35 degree. Now, assume that the pipe is made of carbon steel. So, that once we know what is the material, then we know the thermal conductivity of the material, and the heat exchanger is insulated against the heat losses. That means, this part of the exchanger is insulated. So, there is no external heat, and we need to calculate the number of hairpins. So, with this information, let us try to solve this numerical problem. So, first of all, what we need to find out is the average temperature of the water. So, here we have been told that the hot water is entering at 140 degree centigrade, and the other end of the fluid, I mean when it is coming out, it is only 15 degree temperature drop is allowed. So, it should be 1 minus 15 degree. So, the other end temperature is also known, and we 125 degree C. So, we take an average between 140 and 125. So, it is 132.5 degree centigrade. So, at this average temperature, we are now supposed to find out the properties of water. So, if we find out the properties of water, we will find the density to be 932.53 kg per meter cube. Then we have thermal conductivity of the fluid as 0.687 watt per meter Kelvin. Then we have Prandtl number as 1.28 and Cp is equals to 4.268 kg joule per kg Kelvin. Mu is also known. Mu has been given as 0.207 into 10 to the power of minus 3 Pascal second. So, these are the fluid properties or the properties of water evaluated at an average temperature of 132.5 degree centigrade, and with this information we now supposed to calculate the different heat transfer and etc. So, first of all, we have been given or we have been told about the mass flow rate of the cold water. We know the flow rate of, we know the temperature difference. So, what we have not been told is the flow rate of the hot fluid. So, let us try to calculate the flow rate of the hot fluid, and this can be done by mH Cph delta T H is equals to mc dot both Cpc into delta Tc. So, we have been told about this delta Th, we have been told about this delta Tc, and we know what are the cold fluid flow rate, we know the Cpc, and we can also find out the delta Tc. So, already we have all the properties known. So, we can from there calculate the mH dot, and this will come out to be 1.36 kg per second. So, Cp is taken as of the cold water, it has been taken as 4.179 joule per kg Kelvin, and we have also taken this is at a bulk temperature of 27.5 degree C. This is an average temperature between 20 and 35. So, we know that cold water is entering at 20 degree C and it is leaving at 35 degree C. So, 27.5 is the average temperature of the cold fluid, and at that temperature we have evaluated the Cpc. So, the Cpc is also known in that equation we have used, and this is how we know the hot fluid mass flow rate. So, if we know the hot fluid mass flow rate, then we can try to calculate first of all the velocity, and or we can also take the g, the mass flow rate divided by the free flow area, and then we can apply this relation g dH by mu to calculate the Reynolds number, or we can also try to find out the velocity by m dot by rho A c. So, here if it is for the hot fluid, it will be rho h A c, and you can find out it to be say 0.673 meter per second. So, once we know the velocity, then we can calculate the Reynolds number as rho u d by mH dot. So, this will come out this will be rho v d by mu, and this will come out to be 159,343. So, this is just nothing but the Reynolds number of the hot fluid. The hot fluid is flowing through the inner tube. So, it is flowing through the inner tube. We know the Reynolds number, it is much more than 2300, and obviously, we can understand that this is a turbulent flow. So, we have to use the turbulent Reynolds number, turbulence correlations, and as we have said that we will be using the Nusselt number at the bulk temperature as I have shown it. This is F by 2 into R e to the power, this is P r, that bulk, divided by 1 plus 8.7 into F by 2 whole to the power half, and P r b minus evaluated at the bulk mean temperature divided minus 1, and this F is related to 1.58 into ln of R d minus 3.28 this whole square. And accordingly, if you use, we know first of all we have already calculated the R e. So, we would be able to calculate the F. So, F will come out to be 4.085 into 10 to the power minus 3, and this value will be substituted to that earlier equation, where we know F, we know R e, we know P r, and we will be able to find out this Nusselt number. So, this Nusselt number NUB is equals to 375.3. If you evaluate it, you will be able to find it out. So, this is just nothing but H I d of the hydraulic diameter H d by K, K of the fluid. So, accordingly we can find out the heat transfer coefficient of the inner tube hydraulic diameter. Already we know that is the inner tube. So, we can find out the H I, and this will come out to be 4911.1 watt per meter square Kelvin. So, to determine now the heat transfer coefficient of the annular part, what we need to do is that we need to find out the Reynolds number, and in the annular space, then we have to use the appropriate correlation. We can again use this correlation, but we may have to, depending on whether we are calculating the friction factor or the what is called the friction factor or the Nusselt number or the heat transfer, we have to use either hydraulic diameter or the equivalent diameter. So, let us first try to find out the fluid properties. As we have said that for the cold fluid, we know that the average temperature is, for the cold fluid, the average temperature is 27.5 degrees centigrade, and at that temperature we have the rho equals to 996.4 kg per meter cube, and we also have K is equals to 0.609 watt per meter Kelvin. Then we have Cp is equals to 4.179 joule per kg Kelvin. Then we have Pr equals to 5.77. So, as the temperature has reduced, now we have the higher value of the Prandtl number, and we have the mu equals to 8.41 into 10 to the power minus 6 Pascal second. So, we have these values to evaluate the fluid properties or calculate the different parameters for the annular space. First of all, we need to find out the velocity. How do we find out the velocity? So, we calculate, we know the mass flow rate, and then we find out the AC and rho. What is that AC? The AC is just nothing but there is this free flow area, this is the cross sectional area, and we can find out this one by pi by 4. This is the inner diameter of the outer one, and this is the outer diameter d0 of the inner tube. So, we will use those two parameters we know already. So, d I square minus d0 square. So, this is the free flow area, and we know the density of the cold liquid. So, we will be able to find out the velocity of the hot fluid. This will come out to be 0.729 meter per second. You can try. And the hydraulic diameter can be calculated as, how is the hydraulic diameter? 4 times that free flow area that just now we have calculated, and that P w, which is nothing but pi d0 plus d I. and we have 4 times 4 by pi d square d I square minus d 0 square by 4. This is pi. So, from here you would be able to find out the hydraulic diameter, and this hydraulic diameter will come out to be 0.0176 meter. Now, the Reynolds number. So, we know the hydraulic diameter, we know the U m rho v d hydraulic diameter for this one and by the mu. So, this comes out to be 1500 021. So, this is also more than 2300. So, we have a turbulent flow region. So, we can use the correlation just now we have given. So, that is equals to N u b related to the same f by 2 R e into P r b, etcetera, etcetera. So, from there if you put this value, you will find that f by 2 is coming to be 3.51 into 10 to the power minus 3, and that Nusselt number at the bulk mean temperature, it will come out to be 89. So, once we know the bulk mean temperature, the Nusselt number at the bulk mean temperature, now we have to find out the heat transfer coefficient for the annular space, or that is H 0. For that, we need to depend on the equivalent diameter. Now, the role of equivalent diameter is coming into picture. So, the equivalent diameter we would be able to calculate it as d I square minus d 0 square divided by d 0, and this will come out to be 0.403 meter if you put all the values. So, accordingly we would be able to calculate the H 0 as Nusselt number into bulk divided by d equivalent. So, from here this will come out to be 1345 watt per meter square K. So, once we know the external heat transfer coefficient, we also know the internal heat transfer coefficient. So, now we should be able to find out the overall heat transfer coefficient, and then we can calculate the heat exchanger surface area. Thank you.